Hello everyone, welcome to the first of two videos dedicated to talk about the binomial distribution. In this particular video, we are going to cover the first half of an in-class problem that deals with using the binomial distribution to compute the probability of getting an exact number of dice falling on a number 5. More concretely, we are told that for this problem setup, we know that we have drawn 10 fair 6-sided dice. What does that mean? Well, this is automatically going to give me information about the total number of observations that I have available. So I know that I have a total of 10 observations available. And I also know that this is a 6-sided dice. We know that when we throw a dice, there are 6 possible outcomes one can observe, numbers between 1 and 6. And we know that each one of them happens with a probability of 1/6. So let us keep that information in mind. And now, we are going to talk about what is the probability of getting exactly 2 dice falling on a 5. So again, we're going to stop a moment to digest the information provided by this sentence here. And what we know here is that the only thing that is relevant for us are the instances in which we get 5. And in this particular problem, we are interested in knowing the probability of getting exactly 2 of those 5s. So here, notice that despite the fact that when I throw a dice, there are 6 possible outcomes, really the only one that I am interested in is getting a 5. So I'm going to be defining as a success every dice that falls in a 5, and any dice that fall on any other number is going to be treated as a failure. I'm not going to care about the specific outcome that I get. As long as it's not a 5, it's considered a failure. We have restricted our space of possible outcomes to observe into just 2 possibilities. Either I get a success or not. And for this problem, I am asking the probability of getting 2 of those successes out of the total of 10 trials or 10 times that I have thrown the dice in total. So for doing this, we are going to be using our binomial distribution formula that looks a little bit like this. So here we have our binomial formula, and the binomial formula tells us something about the probability of observing k, where k is any given number of successes out of a total of n observations that I have collected, assuming that on each one of those n observations, the probability of getting a success was theta. So theta is our estimate of the probability of getting a success on each of those trials. And notice here that because k is the number of successes out of a total of n observations, k can only have values between 0, so that is the least number of successes I could find, right, up until n. So k is a count, only takes integer values, and more importantly, it can only go from 0 to n. And now this is the formula that I am going to be using. And I know it looks a little intimidating at first, but if we take a moment to break down what we have to do to compute this probability, we're probably going to end up realizing that this is much more intuitive than we thought at the beginning. So now we are interested in computing specifically the case in which k is exactly 2, given that we have 10 trials and a probability of getting a success on each one of them of 1/6, right? Because for each particular die that I throw, the chances of getting a number 5 is just 1/6. So let us think of a way in which we could observe that. So let's assume that I have just thrown 10 dice now. So here in these little figures, I have represented the possible outcomes that I could have observed after throwing my 10 dice, such that I have gotten exactly 2 successes, exactly 2 of them falling on a 5. So it could be the case that the first 2 dice that I throw end up falling in a 5, and the remaining 8 of them do not. Now, let us try to compute the probability of getting exactly this result, exactly this chain of events. And before we do that, it is important that we realize that each individual die that I throw is independent of each other. The result that I get on a particular die should not have an effect on the result that I get on the next one, and so forth. So all the results that I get on each individual die are independent from each other, and therefore the probability of getting this chain of events can be computed according to the special case of my product rule as the product of their individual probabilities. So I know that I observed here a number 5 with a probability of 1/6. This is another 5. And these are all cases where I got something other than a 5. So by my complement rule, I know that the probability of getting something other than a 5 is 1 minus 1/6, so 5/6, something like this. These are also 5/6. I just didn't have the space to write them down. And hopefully, we can now realize that what I have written just here is actually exactly the same as what I have here on my binomial distribution formula. Why is that? Let us keep breaking it down. Well, because, we know that multiplication is commutative, so I could group together my multiplications and work them bit by bit. So I could group these two successes together and estimate their probability to be 1/6 to the 2. And I could group together all the failures and estimate the probability of getting 8 failures to be 5/6 to the 8. Sorry. And now, because these are also independent from each other, I could simply multiply them together. And now we can see that what we have written here is exactly what we have here in our formula. And that is what the binomial distribution is telling us. We're going to start by computing the joint probability of a given chain of events that contains exactly k successes, each one of them occurring with a probability of theta. So we're going to multiply the probability of getting a success as many times as it appears in my chain. And then I'm going to multiply that by 1 minus theta. And again, this is just my complement rule. This is just indicating the probability of getting a failure. And I'm going to multiply that by itself n minus k times the remaining of the trials that were not a success. So if I have n observations and I know that k of them were a success, necessarily the remaining n minus k must be failures. And that is exactly what we have here. We're multiplying the probability of getting something other than a 5 by itself 8 times, because we have 8 failures and 2 successes. So I could simplify even further like this. I have simply distributed the exponents here to the numerator and denominator, and then I just add them together here for the case of the denominator. This right here would be the probability of any given individual chain like this. So any individual chain that contains just 2 successes and 8 failures. But now, to get to our binomial coefficient, we have to realize that, well, this is just one of many possible chains that I could have observed. It could have also been the case that instead of being the first 2 outcomes or the first 2 dice that result in a success, it is the last 2. It could be these 2. It could be these 2. Like, there are multiple possible chains that could have resulted in a total count of k equals 2. So now, to account for how many possible orders could I have observed in which I got exactly 2 successes in a chain of 10 elements, I am going to use my binomial coefficient. That is exactly what the binomial coefficient does. It helps us to count the number of possible orders in which these 2 successes could have appeared in a chain of this length. So this is the only remaining part here. We have to compute our binomial coefficient for this problem. So here it is. Our formula for the binomial coefficient. It is expressed with this notation that is typically read as n choose k, so choose k elements out of n. And this is expressed with factorials. So factorials look a little intimidating, but we're going to see very quickly that this simplifies a lot very fast. So n factorial, in this case, would be 10 factorial. It's just the product of every integer between 1 and 10. So something like this. And then for the denominator, I'm going to start with this one here for simplicity. So let me sweep them around like this. Again, multiplication is commutative, so the order doesn't really matter. So I'm going to start by breaking this down. So n minus k, that is 10 minus 2, that is just 8. So 8 factorial should look something like this. And luckily, we can see here that there are elements on the denominator and the numerator that are repeated and that are just there as factors. So we can easily cancel them out and reduce our whole fraction here as simply 10 times 9 divided by k factorial. And we know that k factorial is simply 2 because that is 2 times 1. So now this becomes much easier to compute. Now we have just 10 times 9, that is 90, divided by 2, that's 45. We have 45 possible orders of 2 successes in a string of 10 total observations. So now to go back to our binomial formula, we said that this part here is simply telling us the joint probability of a given chain of events that contains k elements that resulted in a success, each one of them occurring with a probability theta, and n minus k elements that resulted in a failure here, or not a success, each of them occurring with a probability of 1 minus theta. So this is just joint probability of any of those chains of results. And here I have the total number of those chains that I can possibly observe given the setup of my problem. So now what I would be doing is I would simply be multiplying this 45 times the probability that we computed a moment ago. So 45 times this. And if we put this into a calculator, we should see that this roughly gives us a result of 0.291. So we have finally gotten our answer for this first exercise. I will see you in the next video.